So next speaker, Patrick Pichler from Dynatrace. We are colleagues, but I think we've actually never really worked.
Not really.
Not really, yeah. So a couple of things that I learned from you. First of all, I really find the Kubeletosaurus Wrecks really cool. It's a good example of a ChatGPT generated title.
So I did not come up with it myself. So yeah. I got some help.
But you know, ChatGPT really does some good jobs, but don't start creating titles in abstract all the time because we spot this. But this is a really cool example of where this works. You also told me that we're going to look into a dinosaur, kind of the code base of Kubernetes today. And for you, it's also a special moment because you're a new speaker. New on the speaker trail?
Definitely, yes.
Yeah. You did a presentation at the Cloud Native meetup, I believe, in Linz, maybe?
No, it was at the Agile Graz meetup.
Oh, Agile Graz meetup, yeah.
Yes.
But you started with meetups. What we talked about earlier in the Cloud Native Austria session, if you want to become a speaker, a great way to get started is smaller venues, and then you work your way all the way up to KubeCon.
Definitely.
This is your step number 2 to KubeCon. With this, tell us more about the dinosaurs.
Okay, thank you. So great afternoon, everybody. So let me first ask you 2 important questions. Question number 1. Who is here to actually learn something about kubelet internals? Come on, raise your hand. Okay, a few of you. Now the even more important question is question number 2. Who is just here for some funny Jurassic Park related memes and references? Okay, so I will cut out the content and let's just look at memes, I guess. All right, let's get started. So first things first, my name is Patrick Pichler. As Andy mentions, I'm currently working at Dynatrace. There I'm a product security engineer, and it doesn't sound like I have a lot to do with Kubernetes, which just from the job title I would say you're right. But I've been running an internal development platform at Dynatrace for around 2 years. I originally started out as a Java software developer before finding Linux and getting sucked into it, so I would definitely call myself a Linux nerd. And I used Arch, by the way. Just don't question why I'm currently here with a MacBook. Yeah, just don't ask. All right, so let me take you on a journey. This journey started around half a year ago, where some colleagues and I were discussing the implications of setting pod memory limits equals to requests. And I noticed that, hey, how does Kubernetes even enforce those memory limits? So I didn't know, and of course what I will always be doing, try to dig deeper and figure out. So the first thing I did was have a look at a Kubernetes diagram, or component diagram. And there I noticed that kubelet is running on each node, and I knew that it's responsible for spawning pods. So probably this is where I need to have a look. But there is already the first problem. Where does one find the kubelet source code? Now, as said, kubelet, super important component of Kubernetes. There is a Kubernetes GitHub organization, so for sure there is maybe a kubelet-related repo in there. So I went to GitHub, put kubelet into the search box of the repositories, and there it is, kubelet. But after having a look at the README, I noticed that this cannot be it. Since apparently this is just used for component config API types and not anything kubelet related. All right, let's think. Where else could the kubelet source code hide? So as said, it's an integral part of Kubernetes. Why not check out the Kubernetes source code itself? So I went to GitHub, grabbed the URL from there, headed to my terminal, typed git clone, waited 5 to 10 minutes, so it takes ages to clone. It's a huge repo. Open my favorite editor, which of course is NeoVim, which is, by the way, the best editor out there, so sorry Emacs folks. And search for files called, or folders called kubelet. Okay, we got some, nice. Now, since Go is my go-to language, so pun intended, I got to know Go, and there see a lot of Go file endings, so I noticed that, hey, it's a Golang system. I know how to actually navigate in here. Okay, now with the kubelet source code figured out, I would say, welcome to Kubelet Park. Our question was to actually figuring out how Kubernetes enforce those pod limits or memory limits. But to enforce something, we need to first learn how those pods get started. So how does Kubelet even start pods? Now the problem with the Kubelet source code base is that it's rather complicated. And to finish this talk within this millennia, I will cut time short and give you some summarization of figures, stuff I found. So the whole Kubelet startup topic might be its own talk, pretty much. In a nutshell, Kubelet's functionality is built around a struct called kubelet. This kubelet struct has a method called syncPod, which is responsible for coercing a pod from its current state to its wanted state. It's just related to startup. Termination of pods is handled elsewhere, which I don't care since we just want to figure out how pod starting works. Once again, this method is pretty complicated, so I will just give you the gist of it and summarize a few steps. But I would definitely recommend you checking it out yourself. It's not that hard to do, and it's a nice way to learn new things. So let's get started. So the first thing the syncPod will be doing is creating mirror pods for static pods. This is how it more or less looks like in code. As a quick refresher, static pods are a special type of pods. They're created by putting pod YAML files at a specific folder on the node. This folder is specified by the static pod path kubelet configuration option. Now kubelet checks this folder periodically for updates and will create, update, or delete those static pods. Mirror pods, on the other hand, are the representation of the static pods at the API server. They will pretty much show up as regular pods there, with the only difference being that they cannot be controlled by the API server. So if you try to run, I don't know, kubectl delete pod, nothing will happen. So to edit or get rid of those static pods, you need to connect to the node and modify the pod YAML. All right, next thing, syncPod will create data directories for pods. Once again, here's how it looks like in the source code. Pod data directories are special folders on the node which Kubelet uses to store some pod-related state. This pod-related state includes the effective host file as well as resolved secrets that will be mounted as volumes, for example. So you can definitely connect to the node, open your favorite file editor, and navigate around these folders to check them out. Now, sorry for breaking the storyline here. Fun fact about this scene. So you might think thinking that this is just some Hollywood made-up way of using computers, but it is actually a quite accurate representation of the Silicon Graphics 3D file navigator for IRIX, which is some Unix-based OS. So this is real. So thank you, Nico, for letting me do all this very important fun fact. Okay, now with that out of the way, syncPod will now fetch some pull secrets. Once again, here's the code for it. Now, how many of you here have tried to run a pod from a static registry and forgetting to actually specify the pull secret? Okay, quite a few. So for those of you who don't know what will happen then is that the container registry pretty much will tell you, you didn't say the magic word. And your pod deployment will fail. So the pull secrets are used to authenticate with the container registry. You can specify them by using the image pull secrets field on the pod spec. And here's how it's used. Here can we see it in action. Okay. Last but not least, syncPod will call the container runtime syncPod method. And this is where the real magic happens. I know it's getting complicated with all these syncPod methods now, so yeah. Okay, the container runtime is pretty much a field in the kubelet struct, which is of type kubecontainer runtime. And if you trace down all implementations of it, you will find that only one is pretty much related to not testing. And this one is called kubegeneric runtime manager. Now, if you have a look at the syncPod method of this kubegeneric runtime manager, you can see that once again, it is doing quite a few steps. The first thing which is actually happening here is now that it will calculate now the actual steps or actions required to get the pod for real this time into our wanted state. I will spare you the details of this method since I was not that interested in it, to be honest. But once again, check out the Kubernetes source code. Pretty interesting read. We will also skip over steps 2 and 3, since those are related to killing pods, and we are interested in studying them, or killing containers. Now, step 4, there's something interesting here. So, what exactly is this pod sandbox? I've never heard about it before, to be honest. Now, if we look at this create pod sandbox method, we can see that it's calling some run pod sandbox method on the runtime service. And once again, tracing down implementations, only one not related to testing, usual blah blah. We can figure out that the implementation for this is called remote runtime service. Okay, the name already kind of hints that this is probably communicating with something outside of our current process. And the code doc mentions, or at least hints, that it is using the gRPC interface. The thing here is that this struct is located in a subfolder called CRI or CRI, or however you want to call it. And this kind of rang the bell. So I saw this somewhere on a cube diagram, but I wasn't sure exactly what it is. That's why I hit it to the Kubernetes documentation and searched for CRI. And hooray, we got a hit. Now the documentation mentions that the CRI is used by kubelet to use a variety of container runtimes without the need to recompile cluster components. It also mentions that it is used as a protocol for communication between kubelet and the runtime. So in a nutshell, this means that the CRI acts as an abstraction over the container runtime. And here's kind of how I imagine it. So the container runtime exposes some kind of API, which adheres to the CRI interface, and kubelet calls them. Okay, all good. But next problem. What exactly is this container runtime? Judging from the name, I guess it runs containers. So, okay, but just to be sure, let's once again hit the Kubernetes documentation. And there it says that, indeed, it is responsible for running pods on your nodes. So it is responsible for running containers, more or less. The documentation also mentions some examples of container runtime. The most famous one being containerd and CRIO. But it also mentions kata containers, which I personally find interesting, since instead of using local Linux namespaces and C groups and whatnot, it uses small specialized VMs for spawning your pods. Sounds pretty cool. Now, what about Docker, you might ask? So here's another fun fact. Docker's API, to be more specific, isn't actually CRI compliant. So it could only be used through a component called Docker shim. Now the problem with it is that it was deprecated in Kubernetes 1.20 and then finally removed from Kubernetes 1.24. But as famous mathematician Ian Malcolm once said, Docker finds a way. And this way is Dockerd, which rhymes, funny name. As the name already kind of hints, Dockerd is a wrapper or adapter around the Docker socket. So in reality, all it does, it exposes its own socket, which then can be called by kubelet, which is then in turn translated to Docker native API calls. All right, now with the container runtime and the container runtime interface out of the way, let's go back to the component which started this investigation of this mysterious rabbit hole, the pod sandbox. Now this is where things get a bit fuzzy. I couldn't find any official documentation what a pod sandbox is, so all that we'll tell you now is what I figured out by looking at the container runtime interface and the containerd implementation myself. And so take all of this with a grain of salt. As we all know, all containers in a pod share a single network namespace. I'm talking about Linux namespaces here and not Kubernetes namespaces. A Linux namespace in a nutshell is a Linux kernel's way of segregating resources. All right, container runtime then also use a special container called a pause container, which in a nutshell is waiting the whole day and just keeping the network namespace open. It has a second job, but we just ignore it for now, which is because it's not that important to our current investigation. But yeah. Now, containerd then treats the pod sandbox as a wrapper around the pause container and this network namespace. It is then provided with a unique ID and handed back to kubelet. So kubelet can reference it later to spawn containers in your network namespace. If you happen to have any more information on this topic or be an expert on this, I would love to have a chat and learn more about this. Because as said, I come up with this myself through looking through containerd sources and the container runtime interface. And unlike the hungry T-Rex Rexy, I will not eat you for lunch. So don't be afraid. Awesome, so this was the pod sandbox. Now back to synced pod. The only thing which is left to do here is the actual starting of containers. And this is done by a local start method, which in turn calls the start container function of the kube generic runtime manager. So let's have a look at it. The first thing which jumped right into my eye was this image pooler ensure image exists. I will spare you once again the detail, but what is happening here behind the scenes is that this image pooler component calls an endpoint on the container runtime interface, which in turn then downloads or do whatever with the image that the container runtime wants. If you think about it, it's the only real way of doing this, since the container runtime is the only place to know how it wants those images. So kubelet will just instruct it to get it. Next, some kind of container config is generated. And if you have a look at it, we can see that this container config specifies the image which will be used for the container, the command, as well as some mounts and devices, and last but not least, some OS-specific settings. Now, having a closer look at the Linux container config, we can see that it once again allows us to specify more resources, which are the CPU period, the CPU quota, CPU shares, the memory limit in bytes, as well as some huge page limits and many more. Now, if you've run a pod before, you've probably used or hopefully used a security context. So the fields in the security context hopefully don't get a very surprise, since they allow you to specify the kubelet, which capabilities are used, if the names or if the container should be run as privileged, as well which user or group is used for running the container. All right, so what's about the Windows config? To be honest, I didn't have that close a look since, yeah, I said I'm a Linux nerd. And in the end, it's the same as Windows, and yeah, without a few special knobs. But anyway, back to start container. Now, the only thing which is left here are the create container and start container methods. Now, both of those are actually thin wrappers around the container runtime interface, which just take the pod sandbox as well as the container configuration, and then instruct the container runtime to spawn the containers. All right, this is how kubelet spawns pods and containers. Now back to our original question. How does now kubelet enforce those memory limits? And the answer to this question is a bit disappointing, to be honest, because kubelet more or less doesn't do that much, besides just specifying the memory limit in bytes in this Linux container resource. Now, the reason for that, if you think about it, makes a lot of sense, since, as mentioned, the kubelet doesn't know which underlying system or technology is used to actually spawn those containers. So how would it, for example, imply some resource limits on, let's say, the micro-VM spawn from Kata containers? So it's the job of the runtime to enforce those limits. So we did it. Finally, yeah, nice. Now, summary time. What did we learn so far? Or what did we learn today? So first of all, the CRI specifies an API how kubelet can interact with the container runtime. We also learned that there are various implementations of container runtimes, with Trio and Container B being the most famous ones, and Kata containers being a honorable mention. We also learned that the container runtime is actually running those containers, and that resource limits are imposed by the container runtime and not kubelet itself. Now, as you can imagine, I gathered quite a lot of content while performing this research. So I can definitely make more than just this talk out of all of this, and I'm actually planning on writing maybe a whole other talk on the kubelet startup process, as well as a blog series. So be sure to check out patrickpichler.f, where I will publish this content. Just don't be surprised, it kind of looks like this currently, so not a lot is going on there, but hopefully there will be content soon. Now, with that said, I hope you learned a thing or two, and if you have any questions about container runtimes, or want to learn some amazing facts about Jurassic Park, since I spent quite a lot of time researching those in the preparation of this talk, be sure to hit me up later and let's have a chat. Thank you.
Really amazing for your second talk, right? You did this at the Agile meetup and now here. Obviously, we should ask you how to find all these memes. But William, from my curiosity, I think maybe you mentioned it, but repeat, why did you start down this rabbit hole? Why did you go down all this way? What was your initial motivation?
As said, so we tried to figuring out were discussing the implication of setting pod memory limits equals requests. And in the end, it was just my curiosity saying, hey, I don't know this, I want to know this. Let's try to figure it out.
Cool. I haven't seen so many code samples in a 20-minute presentation like today.
It was pretty hard to get them all under.
So. Well done. Question time. So folks, whoever has questions, we have a question runner. Please raise your hand. Here we go. Where is third row. Here it is.
Hi. Thanks again for the great talk. I just wanted to know, just the memory limits are set by the container runtime, right? The memory requests are handled by kubelet still.
This is not, in theory you're right. So before, I think a feature introduced with Kubernetes 126, memory requests were more or less discarded, and just limits were set. But with, I think 126, I do not recall the exact versions, kubelet will now specify, or will now hit up the C groups to actually reserve the memory you have in the requests. So you're right, kubelet is responsible for doing this.
But wouldn't, if you specify memory requests, wouldn't kubelet decide if on a node is enough memory free to schedule the pod there or not?
This is not done by kubelet, but it's done by this Kubernetes scheduler. So it knows about all the resources and does the scheduling.
Okay, got it. Thanks.
Welcome.
All right, any other questions? It's a little hard to see always the hands because there's so much light here. Here we go, next row.
So when I'm running an unprivileged container, or running Kubernetes on an unprivileged container itself on an unprivileged container, it often complains that it doesn't have access to a specific kernel feature with out-of-memory killer. And I wanted to ask if you have any experience with something like this.
To be honest, I don't, sadly. But sounds interesting, so if you want, we can talk later. Maybe I can get some details. Maybe we can answer something there.
But if anybody has any experience in this, find the gentleman. What's your name? Carl. Find Carl. He is interested in that, and I'm sure there will be others. And you can easily do this with the beer, because with more beer, there will be more creative answers coming to the whole thing.
Paul must speak, yeah.
And what you should do while Katharina is going up, go back to your website, because one thing you learn as a speaker, make sure that people know how to connect with you later. And
you want to see this
that's
actually.
exactly. patrickpichler.dev. And now the next question.
So I'm just asking the question to get the meme in. So you spared no expense while going to the source code. Thank you.
Exactly.
The resource requests are kept just for scheduling, and the limits are enforced by Linux, right?
Yes, more or less, yeah, exactly. So if you actually want to know more, the problem is that I only had 30 minutes for this talk, so I had to cut quite a lot of things. My original research also included exactly this question. So what if, for example, you don't have memory limits equals request, and your node runs out of memory? How would Kubernetes or kubelet then react? So there's like a whole lot of other stuff in there going on. But in the end, in a nutshell, kubelet will then kill a pod if it goes over its request, and then make space to schedule whatever other pod the kubelet or Kubernetes wants to schedule, more or less in a nutshell. But as said, if you want, we can have a chat later, and I can discuss it in more detail with you.
And on that topic, you may have seen him around, Henrik Rexit. He's actually responsible for these cool videos we have here between the sessions. He is Mr. Is It Observable? So if you go to isitobservable.io, he's doing a lot of videos and tutorials on Kubernetes, especially also around performance, site reliability engineering, and he had a couple of sessions on memory limits, resource limits, request limits, so he's running around somewhere. Maybe he's even here, but I think he's doing some interviews with the speakers. So Henrik Rexit, Swedish guy living in France, you'll have fun with him. Any other questions? All right, then I would say, thanks again, Patrick. Big applause once more.
Thank you for having me.
And we go into a short break, and we will be back at 3 o'clock with Cheap Routes, Fast Paths, and Keeping Track by Lou Conde. He's a senior developer advocate at AWS. See you in a bit.